Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And again, there's going to be a little bit of math in here, but I will try to make this as simple as I can. And I'm just trying to explain a concept, and it's just tough to do it without at least showing a little bit of mathematics. So I apologize in advance for those of you that do not care for that. But anyway, let's go on ahead. We're going to talk about waves in the upper atmosphere that have really long wavelengths. They're very broad, and why they move, or at least can move, sometimes from east to west as opposed to the normal motion that we think of everything coming from west to east. So let's go on ahead and get started here, with a couple of concepts. First of all, there's something called relative vorticity. Vorticity, of course, meaning spin. And think of relative vorticity as being the amount of vorticity in association with everyday weather systems, okay? When you have an area of low pressure, you have high amounts of relative vorticity, or high positive amounts. And when you have an area of high pressure, then that tends to be negative, okay? Then we also have vorticity caused by the Earth's rotation. We call that the Coriolis parameter, but you can also think of it as what we call planetary vorticity, which is the vorticity generated by the Earth's rotation. Okay, talk more about that in just a little bit. H is going to be the depth of the layer. In other words, from the ground all the way up to the top of the atmosphere, or really, in the case of weather forecasting, the top of the troposphere, which is where 99.9% of the weather occurs. So, the change with time, okay, that's what ddt means, of the sum of the relative vorticity and the Coriolis parameter divided by the depth of the layer has to be 0. In other words, this, what we call potential vorticity, has to be conserved. So the addition of those two divided by this has to be 0, okay? Now, let's assume in this case that H is constant. Now, if the air is moving over a mountain range, you can't do that. But let's say that we're out in the Great Plains, everything's flat, and so H isn't going to change. So if H doesn't change, that means that if the relative vorticity, which is this right here, decreases, then the planetary vorticity has to increase, and vice versa, okay? So these two are, I guess you could say, inversely proportional, okay? This goes up, this has to go down, and vice versa, okay? Now, the Coriolis parameter, or planetary vorticity, is equal to 2 times the speed of the Earth's rotation times the sine of the latitude, okay? So the sine goes from 0 at 0 degrees to 1 at 90 degrees, okay? So there is no planetary vorticity at the equator because the sine of 0 is 0. But the planetary vorticity increases from 0 at the equator to higher and higher values as you head north, and it reaches a maximum at the North Pole, okay? Does all that make sense so far? Okay, the other thing that I need to talk about before we get into the wave motion is something called cyclonic and anticyclonic curvature, okay? In the northern hemisphere, if you have air that is blowing around a high, okay, like so, then that is called anticyclonic curvature. And if it's curving in a fashion that would be consistent with it going around a low, that is called cyclonic curvature, okay? So keep all of those concepts in the back of your mind. So here we have what I would call a pretty darn long wave, okay? There's a ridge axis here, and there's another ridge axis way out here in the Atlantic. So this is a very long wavelength, really more than the width of the United States. So let's focus in on the area between the ridge axis and the trough axis, okay? You have high levels of planetary vorticity at high latitudes up here, and low values down here closer to the equator, okay? Let's just say that the air is moving, well, the air is moving in this case, in between these two dotted black lines, there is a component of the wind that is blowing from north to south, okay? There's no component of the wind that's flowing from south to north, but there definitely is a component moving the other direction. So think about an air parcel, if you will, or a pocket of air that is moving southward, okay? It is losing planetary vorticity, okay, because the Earth's rotation causes less and less vorticity as you head toward the equator, which means that the amount of relative vorticity has to be increasing in order for that change to be zero, okay? So you're actually trying to carve out more and more cyclonic curvature between these two dotted lines, and what ends up happening? The wave, the long wave that you see there, actually retrogrades back to the west because you are causing an increase in relative vorticity all along this area in here, okay? So it's carving out a trough, and so the propagation, if you will, appears to be from east to west. Instead of the trough axis being here, now it is shifted back in here, okay? And I've actually seen a little bit of that going on over the course of this week, and what appears to be going on into next week is that when the ridge was in western North America, then the trough was in eastern North America, but more and more that ridge axis is beginning to shift westward out into the Pacific, and that allows the trough, instead of being along the east coast, to amplify in the nation's midsection, and that not only puts us in a position for milder weather, but also in a position for rising motion, and therefore the possibility of clouds and rain, and all of that is in our forecast because of the movement of these long waves. Okay, I hope that made a little bit of sense. I'll try to make sure that Friday's bonus video is just, pictures and no math, okay, to make up for my sins of the last two. And so that is it for now. I hope you have a wonderful Wednesday evening, and we'll talk to you again tomorrow. Take care.